Recall the definition of the derivative of a function f. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. What this computes is the slope of the tangent line of y equals f of x at x. This definition is extremely important to remember as we move through the topics in this course. In practice, though, we do not usually use the limit definition to find the derivative of functions. We have provable rules that let us compute derivatives quickly. These are what we're going to learn next. For example, consider a constant function, f of x equals c. At every x, f isn't changing, so the derivative is 0. We can also use the limit definition of the derivative to check this. Since f is always equal to c, f of x plus h equals c, and f of x equals c, so the top becomes 0, meaning the limit itself will be 0. This is our first derivative rule. The derivative of a constant is always 0. The second rule is called the power rule. This says that the derivative of x raised to some constant power n will be n times x raised to the n minus 1. It can be helpful to think of this as a process. We bring down the power, then subtract 1 off the power. The linear function x is a special case of this. The derivative of x is the derivative of x to the 1, which would be 1 times x to the 0, which equals 1. A couple more quick examples. The derivative of x to the 4th is 4x to the 3rd. The derivative of 1 over x is the derivative of x to the minus 1, which is minus 1x to the minus 2. To find the derivative of the square root of x, we remember that this can be written as x to the 1/2, so the derivative is 1/2 x to the minus 1/2. As long as the power is a constant number, you can apply the power rule. For example, the derivative of x to the pi is pi times x to the pi minus 1. Notice that x is the base part of these functions. If you flip the base in the exponent, you get an exponential function. You cannot use the power rule for these functions. They have their own rule. The derivative of a constant a raised to the x is natural log of a times a to the x. Notice that a needs to be positive for this to make sense. A special case of this is e to the x. The natural log of e is 1, so the derivative of e to the x is e to the x. It may seem strange that the derivative of e to the x is itself, but it makes more sense if we look at its graph. E to the x is always increasing, so its derivative needs to be always positive, just like e to the x. The graph gets steeper as x increases, so the derivative needs to increase more and more as x increases, just like e to the x. Finally, the slope of e to the x flattens out as x gets more negative, so the slope tends to 0, which means that the derivative needs to tend towards 0 as x gets more negative, which is just like e to the x.